In this video, we will get started with our coding activities and we will first develop a multiple layer neural network for a binary classification problem. Now, if you recall, there are two types of, or basically three types of learning algorithms: supervised, unsupervised, and reinforcement learning. And in supervised learning algorithms, we have further two categories: regression algorithms and classification algorithm. And within the classification algorithms, we have the binary classifier and a multi-class classifier. So basically, in this video, we will develop a binary classifier. And for this purpose, I have chosen a data set which is called as ionosphere data set. And this data set describes the radar returns where the target was free electrons in the ionosphere. Now, this is a binary classification problem, and as you move to the last column of your data set, that is here, you could see that there are two classes, G and B. G stands for good and B stands for bad. So in this particular binary classification problem, the positive cases, that is G for good, shows evidence of some type of structure in the ionosphere, and the negative class, which is represented as B for bad, shows the evidence that there is no structure in the ionosphere. So this is a pretty good data set to get started practicing our neural network with Keras, because all of the inputs, if you look into this data set, you can see that all the all the values and entries in this data set are small numerical values, and they relies or they are in a particular range, right? So it is in a range between I believe -1 to 1. And there are of course 351 records or observations, or what we call as rows in your data set. There are 351 rows, and if you count the number of columns, you have 34 attributes. So attributes or features. So the final target Y value does not count as an attribute. So excluding this, there are 34 attributes, or what we call as features in this ionosphere data set. So let's get started and use all the concepts that we have studied so far to build a good binary classifier. So I will be working on my Anaconda Navigator. Now, if you are someone who is beginner in coding, you would preferably want an Anaconda Navigator as an interface. And if you look here, I have like 3 different environment configured in my desktop. So usually it's more than this. I just deleted few of the environments. So I have my base environment, wherein which I have my default TensorFlow CPU installed, and then I have my GPU TensorFlow, wherein which since my computer has a GPU support, I have also installed the GPU version of my TensorFlow, and there is also one more version of GPU TensorFlow with a different initialization setup. So since this is more or less a smaller network that we will be building, I'm just going with the CPU version of my TensorFlow that is available. So, and I will be explaining most of the codes using the Jupyter Notebook interface. So let's get started. So before even we can get started, as I have mentioned in class meetings, we require a TensorFlow installed on our computer. Now, if in order to check if the TensorFlow is correctly installed, what you can do is just ask to print the version of the TensorFlow. So this in my base environment, as I mentioned, I have a TensorFlow CPU, and it is a very old version, 1.1.3. right? Now again, if you have installed a GPU version of your TensorFlow, and you wanted to make sure that it is installed properly, what you can do is you could just use these two commands, that is GPU_available and build with CUDA. So basically, if you have already installed the GPU version, you know that it requires a environment called as CUDA for its installation. Only then you could have a GPU TensorFlow setup. So currently, as I mentioned, in this environment, I'm working on a CPU version. When I print this command, it gives me false. So definitely it should be false because it's a CPU environment I'm working on. So let us go back to my Anaconda interface and change this environment to my GPU environment and come back and check this code. So now I am changing my environment to my GPU TensorFlow. So let's see. So as you can see, when now I have checked my TensorFlow version. So in my GPU environment, I have a latest version of TensorFlow, which is 2.0. And then I will run whether it has been correctly installed. So I can run these three statements. You don't need to have these two statements. If you have this one, this will work. So it's the same statement. So now you can see that it shows me true. That means my GPU version of the TensorFlow with CUDA has been correctly installed on my computer. So before you even start running the code or working on a code, make sure that you have the TensorFlow GPU or CPU version installed on your computer. So let us build our first multi-layer perceptron model for a binary classification problem using an ionosphere dataset. Now, the first step to start any programming in machine learning and neural networks are to import all the necessary libraries. So these are some of the good practices you can follow along so that it makes life easier for everyone. So I have imported all my libraries. So I have my pandas library. I need to load my sklearn library because from there I am using a particular model for dividing my training data set into train and test. I'm also using a label encoder from the sklearn library. So label encoder, as you should have already known by this point, that label encoder is used for encoding or converting a text data into a numerical value, right? And then I have my TensorFlow.keras. So if you remember from the last video, I have mentioned that the Keras open source projects work in two different ways. Either you can use it as a standalone Keras library, or you can use it as tf.keras or TensorFlow.keras, as I have used here, TensorFlow.keras. So this Keras API is integrated into your TensorFlow 2.0, right? So that's what I will be using. So I am using my Keras API integrated into my TensorFlow environment. So that is why I have used TensorFlow.Keras. Also, you should remember from my last video, I have said that the focus of Keras is to have this idea of building a model, and the main type of model is the sequence model, right? The sequential model or the sequential model API. We also have a functional model API, but sequential model API is the one which it's user friendly, so we will go with the sequential model API. So that is why I have imported sequential, right? And then of course the next step is to load the data set. So I have loaded my data set into a pandas data frame called as DF. Once that is done, irrespective of any data set, you have to perform the data processing operation or data pre-processing operations. So depending upon this upon the type of data set you are using, you will use different pre-processing operations. So the first thing that I have done is, which again, irrespective of what your data set is, you should have to do, is to split the input and output columns. So as you might remember, our data set is a binary classification problem, and this last column is my Y value or my target value, and all the remaining 34 columns are my attributes or my features, right? So what I'm doing is I'm extracting all my columns from the first column to the second last column into my X variable and my last column into my Y variable. So again, at this point, I assume how you know to manipulate your data set with the help of pandas data frame, right? So -1 means it refers to your last column. So what this means is everything except your last column goes to the variable X, and your last column goes to your variable Y. So you have now the correct X and Y column, or your input column which has your 34 attributes, and your output column which of course have two sets of values, which is G and B according to our data set. The second step, which is more inclined to this data set, is to ensure all your data sets are floating point values. Now as you can see, some of the values, this is an integer value 1, whereas if you take this value, it is a floating point value. So it's a good practice to convert all the values into the same nomination, and we have decided to convert it into a floating point, right? And then we need to encode the string to integer. So this is where the label encoder function comes into play. So you know your neural network cannot understand, or any of your machine learning algorithms cannot understand anything that is represented as a text, right? So if you look into your target Y column, you have G and B, which are text. So I needed to convert this G and B into a numeric value. So that is why I am using my label encoder function, right? Now you have different other methods for converting strings to integer. Label encoding is just one method. You have one-hot encoding. So again, I assume that these are things you already know. And so I have converted my Y into my numerical forms. So After that, I need to split my data set into train and test, right? So that is why train underscore test underscore split is my function. That again comes from my sklearn library, right? So here I have given my test size to be 0.33. So 0.33, whatever from my total data records. So we have a 351 records, of which 0.33 of percentage of that record goes to your test data, and the remaining will be assigned to your training data. And then I'm printing the number of features. So again, number of features, as we have seen from our data set, should give the output as 34, because we had 34 features or attributes, or 34 column, excluding the last column, right? So when you run this, I have asked to print some of the details. So as you can see, this is my training data shape. This is my test data shape, and for my training data, this is my y value shape, and this is my y value shape for my test data, right? And it agrees with what we see. So 235, this 235 matches, 116 matches with 116, and of course the 34 matches with 34 here, right? So we have pre-processed the data set correctly. Now once we have done that, it is time to the final step, that is to go through the life cycle of a Keras model. Now again, in the previous video, we have looked into the 5 different stages of a Keras model. So first one is to define the model, second one to compile the model, third is to fit the model, fourth to evaluate the model, and finally to make prediction. So let us go step by step. So first is defining the model. And if you remember, this is where we talked about the sequential API or sequential model. And so I have my sequence function called here. So and I have assigned it to a name called model, and then model dot add dense and my layers. So this is my first hidden layer. So this statement refers to my first hidden layer, this statement refers to my second hidden layer, and this statement refers to my output layer, right? So this is the importance of having a sequential or a sequential API model, because now I am able to stack one layer on top of each other as like this, right? So automatically the output of your first hidden layer will go as input to your next hidden layer, and the output of your second hidden layer will go or pass to your output layer. So you don't have, if you were not using this sequential approach, what you will have to do is you will have to assign this line to a variable, say A, and then use this A as input to this layer and assign it another name, say B equal to, and then use this B variable or pass this B variable to this third output, to this output layer. So this avoids a lot of work if you just use the sequential API. So it will automatically pass the output of your first layer as the input of your second layer, and so on, right? Now let us go into our first hidden layer, which is represented by this line. Now of course the input to your first hidden layer comes from your input layer, right? You have your input layer and then your hidden layer. So the input to your hidden layer, first hidden layer, actually comes from your input layer. And from the input layer, so I have the keyword input underscore shape, and that is equal to n underscore feature comma. So what is n underscore feature? From here it is the 34 columns from my data set, right? And it is given as a vector. That is why, so remember, one dimensional array, that's why it is given as n underscore feature comma. So your input underscore shape will only reflect the number of columns. So in our case, the number of columns is present in the variable n underscore features. Now, you might be wondering that even though my data set is like a two-dimensional data set with approximately 315 records and or 351 records and 34 columns. Why is that I'm not taking into consideration the number of records when I provide that it to input shape? Or in short, why don't I give this input shape to be, say, something called as the 351, which is the number of our records, comma 34, which is the number of columns. The answer is that the number of rows in your training data is not a part of the input shape of your network, because the training process feeds the network one sample per batch, or more precisely, batch size samples per batch. Right? So in short, the number of records does not matter when you provide input shape, because it depends upon the batch size that you provide during training, which in our case is 32. So in our first hidden layer, whose input has to come from the input layer, we have the input shape is equal to n underscore features. So my first hidden layer, as I have mentioned, has 10 nodes, and the activation function I am using is ReLU, and the kernel initializer I am using is HeNormal. Now, in one of the videos, I have talked about weight initializations, right? So kernel initializer is the keyword by which you will initialize one technique for weight initialization. So, so if you go back into this page of TensorFlow, you can see that there are many methods of weight initialization. So why do I need a weight initialization? Is that during my forward propagation, I need to calculate the final cost value, or my final error, right? And it is based on this error that my weights get updated. So during my forward propagation, based on whatever weight initialization technique I have chosen, for example, if I have chosen a random initialization, that means during my forward propagation, my weights to my neural network will be some random integer values, right? And based on these weight, my final cost or my final error value which I get after my forward propagation will be calculated. And during the backward propagation, this random weight will be adjusted in order to decrease my final error value, or decrease my final cost, or to optimize my cost, right? So you have different method for initializing the weight, and HeNormal, as what we have used, is one method of weight initialization, because in order to do my forward propagation, I need to have some weight initialized for my network, and I am using a HeNormal technique. So that will, based on the mathematical formula included in that He normal calculation, the weight will be initialized into my network so that I can carry out my forward propagation, and during the backward propagation these randomly initialized weight will be adjusted so as to decrease my error, right? And after that, the output of my first hidden layer goes as an input to my next hidden layer, second hidden layer. And as you can see, the second hidden layer has got 8 nodes. It again uses the activation function ReLU and the weight initialization He normal. So in this network, I just have 2 hidden layers, and then I have at the last my output layer. So as you can see, since this is a binary classification problem, I have my output layer having just 1 node, right? And the activation function I should use is sigmoid activation function. So that's the activation function you will use for a binary classification problem in the output layer. So to sum up what we have just said, so I have my input layer here. So this is my input layer. So this is my input layer, and then I have my first hidden layer. This is my first hidden layer, and this is my second hidden layer, and then of course I have my output layer. And since it is a binary classifier, as you can see in the output layer, I just have 1 node. Now in the input layer, my input shape is 34, and where this shape comes from is based on the number of columns or attributes in my data set. Now this input goes as the input to my first hidden layer, and my first hidden layer, according to the code we have written, I will have 10 neurons or 10 such nodes like this in my first hidden layer. Now going to my second hidden layer, so the input to the second hidden layer, as we can see, comes from my first hidden layer, right? And according to what we have designed, in my second hidden layer I have 8 such nodes, right? So I have 8 such nodes in my second hidden layer. And since it is a binary classification problem, at my output layer I will just have 1 node, which will either say be provided with my sigmoid activation function. So this completes our first stage in the life cycle of a Keras model, that is to define the model. Now the second stage, as we have discussed in our previous video, is to compile the model. So in compilation of the model, there are 3 things that we have to do. First is to choose the optimizer. So we have chosen here an Adam optimizer. So it would be based on this optimizer that the weight function will be adjusted, right? And then of course we have to determine which loss function or which cost function that is to be optimized. So I have chosen the binary cross entropy because it is a binary classification problem, right? Now if it is a regression problem, this will probably change into mean squared error because that is the loss function or cost function. And finally, the metrics, the performance metrics that we wanted to use. So since it is a classification problem, I have chosen accuracy, right? So that is the second stage, and then the third stage is our fit the model or the actual training process. So I have to give my training data set its X and Y components, as you can see here. And then the number of epochs. So we have already discussed what an epoch is. So I'm setting it to 150. Batch size. Again, this is something we have already discussed. Batch size 32. So it is usually said that a batch size of 32 is a good one, right? So we use that as batch size 32, and verbose is equal to 0. So we will see what this verbose is in a short, but let's set it to be 0 for now. And then the fourth stage, which is of course the evaluation of our model, right? So that is based upon our test data set, right? And then again, the last and the final step is to give a new record and see what the prediction for that record is. So I have already trained this model beforehand. So its test accuracy comes as 0.90 and the predicted values. So the predicted value for this particular record comes as 0.97. So we will come back to this and discuss about this. But before that, let us go back and talk about this verbose. So now suppose if I change this verbose to be 2 and rerun my code. So see, so when I change it to verbose, you could actually see what is happening in each epoch, the accuracy, the loss as it goes through each epoch. So I will change these two verbose to 2. So let's see what happens. So I will run this. So as you can see, what happens is that this will give me like a record of what my loss and accuracy looks like at each stage. Now, if you just set it as 0, you will not be able to see all these details. You will just have the final print values. But if you are interested to see, you could set the verbose to be 2, right? So if you set it as 0, as I have said, you will not see the processes happening, how the loss value and how the accuracy changes for each of the stages or each of the epochs. You will not be able to see. So as you can see, we get a test accuracy of 0.9%, and the prediction value for this particular record is 0.9%. Now you might get a slightly different result than what I have got because of course the stochastic nature of our algorithm and our evaluation procedures and differences in the numerical precision. So it's often recommended that you run your example few times and then take the average outcome. So again, if you rerun this code, even in your laptop, you will get a slightly different value every time. So as you can see, the model achieves a classification accuracy of about 91% and the predicted probability of 0.9, that the row of the data that I have given, that is this particular row or record I have given, belongs to class 1. Now you might be thinking why I got a probability here rather than this saying that this belongs to class 1. Why is that I'm getting a probability here? Now that is because there is no binary in a neural network, but you only have continuous functions. So in our output layer, we have used a sigmoid activation function. Now, if you recall, the sigmoid activation function is an S-shaped function, right? And the probability exists between the 0 and 1. So my y-axis is 0 and 1. So when you use a sigmoid activation function in your output layer, and then you train your model with enough data and enough epochs, your result will gradually appear or approach either 0 or 1, but not exactly the zeros and ones. So as you can see in this place, it almost reaches 1, almost reaches 0. So usually it does not reach 0 or 1, but almost reaches. So when you take your y-axis for your sigmoid activation function, it is always within the range 0 and 1, right? That's our probability range. And depending upon your the problem statement, you can define the threshold. So I have given, or you can give 0.5 threshold and say that if I get a probability value which is greater than 0.5, then the category is predicted to be 1, right? To be 1. And if it is less than that, it is predicted to be a class 0. Right? So depending upon whether you are interested to get a precision, or if your problem has if your problem statement you are more concerned about the precision, or if you are concerned about the recall, you can adjust this threshold value. So based on what we have set up, like for example, I am saying that if it is something greater than 0.1, it belongs to the class 1, or it belongs to the positive class, or in our case it belongs to the good class G, right? So I say that the predicted value, since I get the probability of 0.9, which is greater than 0.5, which is my threshold value, which I have set for my problem, I can say that this record belongs to my class 1, or my positive class, in our case the G class, or my good class, right? So that is how you interpret your results.